Hi, Peter.
Hey, Carl, how are you doing?
I'm good. How are you?
Great.
So, I think some introductions are in order. My name is Carl Zimmer. I'm a science writer, and I've done a couple blogging heads so far. And I asked Peter Ward to talk with me this week. And Peter is a paleontologist at the University of Washington, has written a whole bunch of books. Peter, how many books have you written now?
I'm up to 15. 15 holding and hopefully no more, but it's in your blood. You know, it's kind of hard to put the pen down, although the finger down, I guess, the key down.
Yeah. So I got to know you, Peter, I don't know, 12 years ago or something like that?
Oh, at least. You were my editor at Discover Magazine.
Yeah, that's right. And we sort of share a fascination with a lot of things, including extinctions and also aliens. Maybe extinctions and aliens together.
I was just thinking that maybe we should combine that. Well, I've seen that movie, right?
Yeah. Well, let's see how this goes. Let's see if we can talk about extinctions for a while and then talk about aliens for a while.
Okay. It's just conversations with you, Carl, are always great for me, so let's just fire away.
Sure. So one of the reasons that I thought it would be good for us to talk was that extinctions are very much in the news again. So, for example, the IPCC report on global warming is reinforcing this warning that the figure, I think, is like 20-30% of all species may be committed to extinction by the warming that's going to take place over the next century if we don't do anything. I also, see reports about how maybe the mammoths and the other big animals in North America may have become extinct because of maybe a comet or an asteroid or something blowing up over North America. It seems like there's a lot of extinction news these days. I don't know if you get that impression.
Yeah, I do. It's actually a topic that never seems to go out of fashion. It would go all the way back to 1800, of course. And the first sense that any extinction at all took place was way back with the Frenchman Georges Cuvier. So, yeah, periodically there have been extinctions, it seems, and certainly periodically we scientists have gone in and with renewed vigor as new techniques have come online, new discoveries are made. And there's implications from lots of fields of study that keep bringing us back to this topic. It's very timely and very important.
So you got into this, if I remember correctly, from your books in the early 80s, right?
Well, even before that, I was always fascinated as a kid by Jules Verne's 20,000 Leagues Under the Sea and that beautiful Disney recreation of the Nautilus. So the name was in my brain as something very cool. And when I saw my first Nautilus shell, I think I was 7 years old. I just became entranced.
And the Nautilus is this. Tell people about the Nautilus, this animal that you love so much.
Yeah, the Nautilus is that beautiful shell, 6 inches in diameter, that has that wonderful spiral. And when cut in half, you see within it a series of chambers. And that logo is used by corporations and art. It's just, you find it everywhere. The creature is a throwback, a living fossil back to 500 million years ago. It was probably the very first large carnivore in the sea. And I very much wanted to study this creature, and did. And the reason, the portal to extinction from Nautilus, is that it did survive 500 million years, whereas its nearest cousin, the ammonites, did not. Now, both of these we can get a mental picture. So imagine a beautiful spiral shell and stick a squid body in it, and that's essentially what you have. The tentacles, they swim around. Mm-hmm. They're not sitting on the bottom like a snail. So these are functional, essentially fish, and yet one big group goes out entirely. Every one of the mass extinctions, of which there were maybe 14, but only 5 are huge in the last 500 million years. How do we call these the big 5? It was the very last of these, the famous KT dinosaur killer, that took out my favorite group of animals, but not the Nautilus. So why did one survive and the other not? Was in the 1970s, I started grad school in 1971, and that was what was driving me and continues to.
So you were spending the 70s studying fossil ammonites and trying to figure out sort of the timing of their extinction and things like that?
Yeah, and other things too. Figuring out how not to get sent to Vietnam as as fodder for whatever that particular war was. But yes, I was in graduate school and very much interested in fossil and recent organisms. So that intersection.
Mm-hmm. Mm-hmm. And I guess when this idea about a asteroid or a comet or something hitting the Earth came along, you talk in your book, I believe in Under the Green Sky, you talk about how that really galvanized you. I mean, you were really excited about that possibility.
Sure, not just me, Carl. You'll remember it was 1980 when this famous Alvarez two-part hypothesis. Really, they were working, or one of them, the son, Walter Alvarez, was working in the Cretaceous age. So rocks, the Cretaceous goes from 65 all the way back to 125 million years ago. Mm-hmm. But the end of the Cretaceous is marked by one of these big extinctions, and he was curious about how long it took. So he's working on rocks in Italy, and there's a very thin layer between rocks with Cretaceous fossils in it and those with the subsequent tertiary level fossils in it, and asked his dad, can you think of a way to discover how long it took for that very thin millimeter thick layer to be deposited? His dad was the Nobel Prize winner, Louis Alvarez, and he said, look, there's a constant rain of comet dust and asteroid dust and space dust falling on the Earth. Mm-hmm. We pretty much know how fast that is, and just if we get a concentration of the extraterrestrial component of the rock you're looking at, we could maybe calculate how long it took. And so they were looking for something entirely different, put it in their machines, and came back with this extraordinarily high concentration. And from that, the great scientific and genius, really, the leap, was that, my gosh, we were hit by a large asteroid, and maybe the hit caused the extinction.
Yeah, I've been working on an introduction to a new edition of Walter Alvarez's book about this T-Rex and the Crater of Doom, and so it gave me a chance to kind of go back to all this. I have to confess I was actually in high school at the time, but so my memories aren't very clear about it, but it is interesting going back and just seeing how strongly people reacted, either very excited about this possibility or saying it was just total nonsense, or just the whole idea that some external thing could just wipe so much of life out.
It caused enormous controversy, but also enormous passion, as you said. I do remember it as the scientifically most interesting and vibrant period, because every year new discoveries were rolling in. From 1980 all the way to 1990, when finally the crater was discovered, every year was a brand new series of meetings, and people were passionate. Reputations literally were going up and going down year by year, and there were smear campaigns. It was just an extraordinary time.
I mean, it's funny. I mean, there are certain things in science that inspire this kind of stuff. I mean, I'm thinking of like the human genome, or the oldest hominid fossil on our own lineage branching off from other apes. I wonder why the death of the dinosaurs was in this league. I don't know.
Well, there's many levels. One is that a lot of this was driven by journalism, and the journalists, every kid in the world wants to know why the dinosaurs go extinct. It's like went extinct. But on a second level, when you think about science and what drives science, this was an attack on one of the oldest and most bedrock foundations of geology, the principle of uniformitarianism, 200 years old. And that principle, from Hutton and Lyell, these ancient British geologists, all the way back to the late 1700s, early 1800s, was that there's nothing extraordinary about the past record of rocks on Earth. In fact, every aspect of rock building can be observed today. And this replaced what was then the idea called catastrophism, that it was a series of sequential catastrophes, floods of the earth or great heating periods, that would wipe out everything and stuff would come right back. God would recreate the world. It was strongly religious, and the whole flood myth was part of it. So here's the Alvarez's coming and saying, oh no, we've never witnessed this. This is a neo-catastrophism. And boy, did that get blood boiling.
Yeah, and they also had this sort of, they also perceived as pretty haughty, these physicists and geologists coming in and telling biologists what's what.
Well, totally. And it was so interesting. I really traced back and you wanted to talk about aliens, I really traced back the first development of the field of astrobiology to the KT. for the first time, astronomers and paleontologists were in the same room. I mean, it had never happened before. And it was such an interesting time because, in actuality, we didn't even know how to talk to one another. It was very funny. I was at a conference where we geologists brought our 35 millimeter slides. You remember slide projectors? And all the astronomers brought these transparencies that you put on overhead projectors. And there was no slide projector, so we had this one-sided astronomical bent on the things. And you're indeed correct. Luis Alvarez set the tone, very unfortunately. He most famously said that when the paleontologists were not coming to and totally supporting him, and it took years to really find out from the paleontological record, he called paleontologists stamp collectors. And he was very in the middle of actually trying to trounce people's careers. I mean, there were some really ugly things that happened through this period.
And it's funny, though, because I think that paleontologists really benefited from this because, I mean, now it's paleontologists who can really tell us about these huge patterns in the history of life. Not someone who's focusing on generation by generation evolutionary change. It's to really these things happen all of a sudden that you can't just sort of project from what's happening right now.
Oh, absolutely. I mean, you're totally correct on this. And but during the fight, it was the paleontologists who were perceived as the bad guys and really the bad scientists.
Right. But you were a paleontologist who was willing to join the dark side, I guess.
Well, it's funny. I had a conversion. My work, you were right. Earlier in our conversation, you said that I was galvanized. The entire field of paleontology was, but I personally was. Yes, indeed. I worked at Davis, California, which is only 60 miles from Berkeley. I was at the University of California, a different branch from the Alvarezes. But more importantly, I was on sabbatical in 1981, 1982, just 2 years afterward. The controversy was in full bloom at that time, and I happened to be, actually, just by pure accident, in a part of Europe where there were rocks of that age, and there were testable series of problems that I could get my particular expertise to work on. It was not so much the extinction of dinosaurs, and up to that time, really, the only creatures that had been examined by 82 were tiny microfossils. But it was mid-sized stuff, invertebrates. And again, here's where my ammonites came in. We know they went extinct then, but did they go out gradually or suddenly? And my first published work, I think, came out in 1983 on this. The rocks I collected, admittedly few in number by that time, but it was a very gradual pattern. So I published this, and I was instantly embraced by the majority of paleontologists and those who very vehemently opposed this whole idea that A, we were hit, and B, the after effects of the hit caused the extinction. The Alvarez is just, as an example, I went and gave a talk at Berkeley, and they snubbed me. They wouldn't talk to me, and they walked out of the talk and on and on. And the funny deal is, by 2 years later, when much more work of mine showed that indeed it was catastrophic, I was their hero. They took me to dinner, wined and dined me. It was strange days. Fun, though. Absolutely fun.
Yeah. So, I mean, so it's been, it's been almost 30 years now since the Alvarez hypothesis came out, and well,
it's under attack again. Interestingly,
yeah. So I mean, in this time, like this image of a, you see this picture. I don't know who painted it, but like of dinosaurs looking off towards the horizon, and this big asteroid coming down and creating this kind of mushroom cloud type thing, and it's sort of almost like this icon of the apocalypse, sort of, I guess, in a way, and yet, there's still the scientific debate. I guess, does it still go on? I mean, what?
Well, yes and no. There's always been one person. Her name is Gerta Keller, professor at Berkeley, and she's always been
Berkeley
opposed.
Or Princeton?
Oh, I'm sorry, Princeton. Excuse me. Yes.
Okay.
The other opponent to it was a man named William Clemens, and he was at Berkeley. But yeah, Gerta continues to this day, and here's her point, and it's a pretty good one, as we'll see subsequent in this conversation. The other mass extinctions have always been associated with flood basalts. These are strange volcanic episodes where you don't have volcanoes like Mount St. Helens blowing their top. Instead, it's more like Hawaii, where you have cracks open up and the lava just dribbles out. But it does so over such large areas of the Earth's surface. It's not the lava that kills stuff, but it's the gases, the volcanic gases, especially carbon dioxide. But here's Gerda's point. It turned out that at the time of the KT, 65 million years ago, one of the biggest of these flood basalts did occur. It's called the Deccan Traps. Now, I remain absolutely convinced that it was the asteroid that did the greatest amount of damage. But, in all fairness, there was a flood basalt. And as we're going to see, the other flood basalts are absolutely related to and certainly coincident with the other mass extinction. So how could you say every one of the flood basalts did it except that particular one? So I suspect there's an influence from the volcanoes, and it may be the extinction was as bad as it was because we had two things happen.
Yeah, I'm always intrigued at how you can sort of try to disentangle all these different potential causes.
Well, I'm not sure you can, really, not yet. Well, people are trying, but it's very, very difficult to do that.
Yeah, so 65 million years ago, right around the time this asteroid hit, so there's a flood basalts in, these are in India, right?
Yeah, that's correct. It's what was going to become India. India was still really an island, really, large Australia-sized block that was heading hell-bent for the Asia, where it would so famously collide and produce the Himalayas as a consequence. But that was still way in the future. So yes, there were the big flood basalts covering large parts of India that had to have had climate change effects on our planet.
So why did they have to have climate change effects?
Well, lots of CO2. Anytime in the past when you heat the planet, changes the climate. We're seeing this now, aren't we?
So the CO2 is coming out of the volcano.
Yes, absolutely, and it's a greenhouse gas. It's not the best greenhouse gas. Methane is better, and water vapor, but it was certainly the most abundant. And we do have records. We can directly measure past CO2 levels by a number of ways, but the most interesting is to look at fossil plants. As you know, if you grow plants in a high CO2 atmosphere, the tiny little holes called stomata that let CO2 enter, a plant absolutely have to have it for photosynthesis. There's fewer of them and they're smaller. They don't need much. But in a low CO2 environment, you have lots and lots of holes. You need the CO2. Well, we certainly have record across many of these mass extinction boundaries that prior to the extinction itself, carbon dioxide was rising and rising rapidly and to very high levels in the atmosphere.
And I mean, and with that asteroid, it comes. It's like 10 miles across or something, right? And
10 kilometers, 6 miles, 6.6 miles.
Okay.
But that's just an estimate, guess that these guys did. But going back to the size of the crater, which is 200 kilometers across.
This is off the coast of the Yucatan Peninsula.
Parts off the coast, parts right on it.
Oh, okay. And so, when you drop something like that on the Earth, I mean, I guess you get a lot of stuff in the atmosphere that way too.
Sure. And one of the things we're always looking for is the actual kill mechanism, and this was really part of the debate. People didn't really know you say we were hit, sure, left a crater, sure, but how could a crater, formation of a crater, change anything to kill anything? And that was a big part of this whole story.
So you have just kind of an ecological collapse from not having any sunlight, from dust in the sky, or what?
Well, let's walk through this. It was very interesting, and again, there's this sense that perhaps where this asteroid hit on the planet may have actually made it much worse than it would otherwise have been. We'll talk about colossal bad luck, and the reason I say that is the asteroid landed in a very shallow sea, but one that had anomalous amounts of minerals, sedimentary rocks that contain sulfur within them. There were rocks called gypsum, there was some anhydrite, there was various types of sulfur-bearing rocks, and down comes the asteroid. And in so doing, it's not the asteroid itself, although you can imagine it's about the size of Mount Everest. So imagine you're throwing Mount Everest at the Earth. Well, big as Mount Everest is, the Earth is still a pretty bigger place. But the crater, if you gouge out a 120-mile wide crater, down to a very significant depth. And just think of how much rock there is in that gouging. Throw that up into space, and here's what happens. The first and most horrible thing that happens is there's a shock wave around the impact site, and that would have killed lots of stuff. Secondly, because it hit in a shallow ocean, it immediately started an enormous tsunami that may have actually been like a wave that bounced off various parts of the basin. But the third horrible thing that came from this, and this is all within the first hour, is over the next hour or so, stuff goes into space. I mean, you throw it, it's like throwing a rock in the water. You see the splash up. Well, all that crater fill goes up. Some landed on the moon. I would guarantee there's pieces of dinosaur bone on the moon from that explosion, or that great impact. But where most of it goes is suborbital. Remember the old Mercury flights? We used to put the tin cans up, the Mercury astronauts. Before we sent them in orbit, we just threw them up and down. They came, and they had to have a heat shield, because re-entry at high speed heats you to the point that unless you had a very good ceramic heat shield, they were toast, literally. Well, lots of that crater infill did become toast. Well, actually, it became fiery rock. It melted. And on coming back, it was at such high temperature, the same temperature as lava, it set the forest on fire. And we have absolute evidence of this, that the forest burned down to the ground, and there was no grasslands in those days. It was a wet, lush world, but not wet enough, apparently, because we have soot, we have charcoal. At every KT boundary section, when you dig out the layer of the impact that was caused by the impact, you find evidence that the forest burned down. And this was probably what caused the majority of terrestrial extinctions, and may certainly have doomed the dinosaurs. What a horrible fate.
Wow. Yeah, it's interesting how there's just this whole craze about meteorites hitting the Earth, and
hey, 2 movies, baby.
Right,
Deep Impact and Armageddon, and they're direct results of this particular finding. And I was at a meeting in 1995. A Spielberg representative was there taking notes as we described what happened.
Was that right?
And I was. It was an interesting meeting. It was with Russians and with the bomb makers. The U.S. nuclear bomb makers were there because they were all trying to figure out, with the fall of communism and the fall of the Cold War, what their jobs depended on finding some new evil empire. So why not the evil asteroid empire? And both sides were talking about how we would attach nuclear bombs, hydrogen bombs, to the tops of our ICBMs and reprogram them to blast these asteroids out of existence, actually nudge them, because you couldn't destroy them, but just move them slightly if one were aimed at the Earth. And sure enough, 2 movies, not one. Deep Impact, which was way more scientifically accurate, and then Bruce Willis. Thank goodness that Bruce, and hope he's around forever. We're going to need Bruce over and over.
Right. So, I mean, science fiction aside, I mean, do you think these near-Earth asteroids are things to really get worried about? I mean,
absolutely, they are a tremendously. It's a threat that won't go away, and because we have a very good sense of how fast and how rapidly and how often these things come down, and luckily for us, big ones like the dinosaur killer. The estimate is that once every 100 million years we should be hit by something but it's really turning out to be much less than that even. In the last 500 million years, one of those things hit but once. But on the other end, how much disturbance would it take to totally disrupt human agriculture? And this is where NASA's work and other people's to identify the near-Earth objects, the NEOs, which are really the Earth crossers. And these could come from several reservoirs. They're either comets, which are the most dangerous, or asteroids from the asteroid belt or various parts of the solar system. But when these things are nudged out of orbit, and this could be the effect of Jupiter, it could be that they are hit, they have a collision with something else. But there's a lot of ways you can nudge them, and if they fall inward and do hit the Earth, even a small one, and by small, let's go back to the most famous impact of certainly of recent historic time, the Tunguska effect of 1906 or 1908.
And that hit over Siberia, right?
Yeah, and it wasn't even a hit. Right. It turns out anything 50 meters in diameter or less will not go all the way to the ground and hit the ground. It, actually, the compression these things are, they're not solid rock. They're just hunks of ice, like a snow cone, and they blow up in the atmosphere called air bursts. But it had sufficient energy that it was way over the amount of energy liberated by the Hiroshima-type atomic bombs. It blasted huge areas, and had that burst over a city, there would have been widespread casualty. Right. And so the other aspect that's really scary is that they do throw up dust in the sky. And the other part, too, of the Alvarez idea, and what we didn't get to, we certainly saw dinosaurs die, but how did the stuff in the ocean? Well, you have an awful lot of dust going up, causing dark nuclear winter, was most famously called by Carl Sagan. But secondly, there's a lot of, because the sulfur went up there, a lot of acid rain came down. So if we had acid rain, dark times, different temperatures on human crops, it doesn't, you don't have to go very long without food for 6 billion hungry people on this planet to get the crash of civilization, and that's the big danger.
What do you think about sort of the state of the art now in terms of trying to keep track of these things? I mean,
oh, we're doing great. Yeah. I actually was in New York the last couple of days giving lectures on this, and I showed the metrics that I have gotten from various specialists that we're really on the downswing. Over the last 3 or 4 years, we've identified the majority of objects that are in Earth-crossing orbits today. We know where they are. We can predict. And as you know, Carl, about every year somebody comes out, Chicken Little, says, we're going to be hit, and then further work shows that we're not. I mean, it's a rare thing, but on the other hand, geological time is a long thing. And so something that seems so statistically impossible becomes probable given enough time.
Yeah, I mean, that's something that I've thought is about in terms of global warming, in terms of a lot of things like near-Earth asteroids. It's like, how do we, I'm not sure how we're going to do our planning. We think ahead a few years at most, if we're lucky, when we might be aware of things that might be a problem 100 years from now, 1,000 years from now. How do you prepare for that?
Good question. How do you keep your... what assumption can we make about the level of civilization? Not the hundreds you can make sense of, but thousands of years from now. Will there still be rockets of sufficient power and accuracy? And will there still be the nuclear weapons? That really is the only way to nudge them. People talk about kinetic, where you throw up big iron hunks and try to break up the asteroid, but it's going to have to be either landing on it as in the movies, and they were quite correct, and blowing off a hydrogen bomb that would nudge it. You only have to nudge it a slight amount if it's far enough away. But can we, 10,000 years from now, 100,000 years from now, can we expect there will be a human civilization that can still detect them and still push them out of the way? I don't know. This is the great unknown, isn't it?
Yeah, I mean, the skeptical voice in me sometimes speaks up at about this point and says, is this just a way for people who study asteroids for a living to get more funding?
Partly. And again, it goes right back to the whole business about the nuclear industry. I mean, the bomb builders, this was another way to justify the continued money being poured into missile development and bombs. And the Russians were there too. The Russians overtly in this 1995 meeting I attended was that their take was that by treaty they were supposed to destroy a bunch of their SS-20 rockets, and they said no, we're going to keep them as a nuclear deterrent against asteroids. I mean, what nonsense. But nevertheless, this was the justification. And as for the asteroid hunters, again, fewer and fewer are being found now because the big ones have been found, but the scary ones are the little ones. You can't track these 50-meter jobs. And here's the scenario that scares us the most. Let's say that tonight an object the size of Tunguska airbursts over Washington, D.C. Boom. And kills off most of the U.S. government, who, strangely enough, isn't on vacation, but they're there. I guess we can't do it tonight. They've probably been on vacation. You see the point. We blow them up. President's dead. Cheney's left. Finger on the trigger. How can the scientists get to him quickly enough and tell him there's no radioactivity, there's no fallout, this was just a burst? And we scientists have had meetings where we're trying to figure out, does anybody have a phone number that could quickly enough tell them, don't take out Moscow or Tehran or wherever you think that bomb came from? And it's a real problem.
I hadn't thought of it that way.
Who are you going to call?
Yeah.
Dick Cheney. Well, here's his excuse, right? I hate that.
Well, I see the movie now. You're in the movie and you're like running down the street, waving your arms, trying to get their attention.
The sky had fallen. The sky has fallen. Really, the sky has fallen.
It's not the Russians.
Nuke. Yeah. Well, boy, I'll tell you, Carl, we laugh, but it's wouldn't be too funny. You could kill easily 10 million people with one of these airbursts. Yeah.
Well, I guess what a lot of people don't realize is something you were talking about before, is that for people like yourself who study mass extinctions, things falling out of the sky really, they're not what keep you busy. I mean, they're not the things that you're really studying that much.
Well, I was. And this is the great second sort of part of this conversation, was that we were doing it in historical fashion. It began in 1980, got to 1990 when the crater was found, and by 2000 we've had the blockbuster movies. But what happens from 2000 on?
Yeah.
And we talked about a lot of mass extinctions. By 1990,
let me back up. What qualifies something as a mass extinction?
Great question. And generally we think if, say, 20 to 30% of the species on the planet are driven into extinction in a relatively short period of time. It sounds like maybe 1 million years or less. That sounds like a long time, but given the age of the Earth, it's not. Mm-hmm. But even 100,000 years. Mm-hmm. And the dinosaur killer, the whole KT may have taken 3 months from start to finish. So a short period when a lot of species die. Yeah. Each of the big ones, 5 big ones, the big 5, killed 50% of species or more, and the largest, the Permian, is reputed to have killed off 90% of species. But I personally doubt that. But nevertheless, it is the biggest, and there was a huge species kill.
So 65 million years ago, the dinosaurs, the ammonites, and I should say the dinosaurs that weren't flying around.
Yeah, except the birds.
The non-flying
those bird dinosaurs survived.
Right. But all the other dinosaurs die off, and a bunch of other, big sea reptiles die off.
Yeah, big stuff. You said the operable word here, big.
Mm-hmm. But about 50% of the species, is that right?
That's the estimate. Yeah. But once again, this is based on how many species that have a fossil record. We don't know about the worms and the stuff that never preserves anyway. We're presuming. There's a lot of presumption and hoping that goes on in paleontology. Yeah. But that's the guess.
And so then this big Permian one, 250 million years ago, is like 90. Well, you're saying maybe not quite 90 now?
Well, I have actually done some preliminary work that suggests it wasn't the 90, but nevertheless, it still was the biggest.
Yeah. I've written about the Permian-Triassic extinction a couple times, and it definitely has not sort of grabbed the public attention anywhere near like the dinosaur extinction, the KT extinction 65 million years ago. It really doesn't. I don't know what it is. Maybe it's just that there weren't big, sexy animals that keeled over.
And that's part of it.
I don't know, but I mean, it was so huge, and maybe it's because it's also complicated. I don't know. Maybe let's talk about sort of what you think is what happened 250 million years ago.
Well, you're totally correct about the animals, although I think that's really, the animals are being shortchanged. There was a predator called a Gorgonopsian. Mm-hmm. The skulls are as large as 2 feet in length. The total animal about 13, 14 feet, most probably smaller, 10 feet, 8 feet. But like gigantic lions that still have a body squatter or something like a crocodile. Think of a long-legged crocodile with a big nasty lion's head, scaly. These were pre-mammals. They had mammal characteristics and reptilian characteristics, and there were lots of them, many species. A whole world destroyed by this particular mass extinction. Luckily, a couple of the little guys get through it because they become the mammals, and we don't have this conversation if that survival doesn't take place. But nevertheless, they're not dinosaurs, and therefore it really hasn't attracted the attention that the very sexy dinosaurs have.
Yeah. So 250 million years ago, actually, like dinosaurs are just getting off the ground, right? And there weren't.
No, they're still a far away gleam in their ancestors' eyes.
So you've just got sort of their reptilian ancestors around, yeah.
Well, we're just getting to crocodiles then. The whole stem group, the archosaurs that are going to give rise to the crocodile lineages, which do survive, and then the big dinosaur lineages, which survive as well as birds. I mean, that big grouping of dinosaurs. Birds are perfectly good dinosaurs. The big ones, though, the iconic dinosaurs, all die out. But they don't get around to getting going until the latter part of the Triassic.
Right.
So you're talking about the Permian extinction is 250 million years ago. Dinosaurs themselves first start up somewhere between 230 and 225. So 25 million years later, there's dinosaurs.
So you've just got reptile-type things crawling around. You've got sort of mammal,
Yeah, they're mammalian-like, and the true mammals arrive at about the same time the true dinosaurs do. But prior to that, you have stuff that looks getting almost dinosaur-like. You've got bipedal guys as well as quadrupeds. You've got mammal-like things that are like big cows walking around, stumbling around. So it's becoming increasingly modern. But then along comes the whole dinosaur lineage, which really takes over the planet. But that's a different story. They get theirs, of course, as we know. But the first big crisis that they and everybody had to undergo was another of these big five, the Triassic, Jurassic mass extinction.
Well, I want to talk about the Permian.
Got it. Okay. They're like bookends.
I want to talk about the big one.
Got it.
So, and it's so in the extinction. I mean, when you look at the fossil record, you're seeing a bunch of these reptilian things on land becoming extinct. Plants, right? There are a bunch of plants.
Lots of plants, sure.
They're disappearing. And in the ocean, it's pretty devastating too, right?
Absolutely. It was so devastating that this was recognized in 1860 by a man named John Phillips. And that recognition led him to the terms we still use, Paleozoic, Mesozoic, and Cenozoic. All they mean is that you got three groups of animals really on planet Earth.
Yeah.
And the Permian extinction ends the Paleozoic. And Paleozoic means old life. Mesozoic, middle life. So catastrophic was it that you killed off almost everything, and therefore you re-evolved an entirely new group of organisms. Big time extinction.
Yeah, so mass extinctions can really they don't just knock some things out. They give evolution a chance to sort of reorganize the whole playing table.
And it not only does it give it the chance, it happened over and over. Yes, you never get the same stuff back.
Right.
You get new lineages, new winners, and sometimes there's things lying in the weeds, just waiting their turn. Like we have these things called brachiopods, which have two shells. They look all the world like clams. But until the Permian extinction, the clams, which are actually, turns out, physiologically superior in many ways, there's an evolutionary incumbency, and an incumbent can be inferior and still hold on to things. Well, once you're knocked off by mass extinction, you reset everything. They're huge scale. They're the largest scale evolutionary events.
I see. Yeah. So it's not. I mean, that's another interesting thing about these extinctions. It's you don't even if you someone might consider you the quote best adapted or the most fit species or whatever that means, you might still get knocked out.
Absolutely. I mean, absolutely knocked out. Yeah, and it happened. And with the impact, there's almost no rhyme nor reason other than the one factor that led to survival was you were small or you lived deep, or on land you were able to bury your eggs or bury yourself, and you weren't big. Dinosaurs just couldn't hide anywhere. Now the other extinctions, there were different factors, but sometimes it's chance, sometimes it was pre-adaptation. You lucked out, but a lot of luck was involved.
So what's your
Permian extinction?
Permian extinction, yeah. So you do a lot of field work for this, right? You go to like South Africa. You go to where else do you go to study this stuff?
Yeah, we're still doing it. We've got a field area now that is in Alberta, way up in the Rockies. Very beautiful place called Opal Creek. We're working through there. I'm working in Australia using cores and Permian aged rocks, and of course my major field base has been since 1992 when I first went. South Africa, the Karoo Desert. And I can't count how many times, but I spent a decade going twice a year to that place and living a rather exhilarating but miserable existence in tents in this desert, collecting these mammal-like reptiles, both before and after the extinction. Look, Carl, in 1990, I was a true believer in impact. I believed every one of the mass extinctions was caused by impact, that all I had to do was go to these other times and places, go to South Africa, dig a trench, and find the same stuff we find that the Alvarez found. We find a thin layer full of iridium, the platinum group element. We find shot quartz, which is the residue of great pressure on small sand grains, and the glassy spherules, the stuff that came back and burned the forest. We find these tiny little tektites. Well, guess what? We never found them. But nevertheless, the irony here is that in 2002, just about the time that I was finally convincing myself, gee, maybe this permanent extinction isn't caused by the impact, along comes a very famous paper by a woman named Luann Becker, who brought a whole new word into our lexicon in geological terms called buckyballs.
So these are these molecules of carbon. They've got like 60 carbon molecules that are sort of connected to each other. It kind of looks like a Buckminster-Fuller geodesic
That's exactly
dome,
right? And more than that, contained within them, the buckyballs are thought to have been caused or formed by the great heat and pressure of the impact, but they're carrying within them pieces of the impactor in the form of small molecules of helium, small atoms of helium, really. It's not a molecule at all. They're just stripped down helium atoms. And this woman very famously showed in Science magazine that she said at 2 places on the Earth's surface she could find this residue of a comet at the same place as the extinction. And the reason I know so much about this, other than obviously professional interest, she was at the University of Washington, where I worked then and work now. I hired her to be a sabbatical replacement for another professor and watched all this unfolding. But there's a very strange twist to the story, and this is where the press, if you ask the average reporter if they know at all about extinctions or care, and the science reporters do, they'll tell you, yep, impact. I had a conversation with Ron Reagan. I was on one of his shows a couple of years ago, and we were in makeup together. And I said, yeah, I work on the permanent extinction. He said, yeah, impact. He's a pretty well-read guy. But the scientists have moved away from impact. We no longer believe. And this whole buckyball story absolutely fell apart. A, her initial results could not be replicated even from the same rocks. And B, she found it in 2 places, one in China, the other in Japan. Well, guess what happened to the Japanese samples? They were found by fossil people who looked at them to not be Permo-Triassic, not be 250 million years old at all. They turned out to be about 210. They were Triassic rocks.
So this whole impact thing kind of...
Oh, it totally fell apart, except among the scientists fell apart. But there's still a sense that it's out there. And the ridiculous ends things go. Last year, I saw a huge splashed headline, "Crater for the permanent extinction found in Antarctica." And
I didn't see that one.
What's the data? Where's the beef, as the Wendy's used to say? And it turned out that this was a guy in a meeting. It wasn't even a published paper. It was an abstract who had recognized from some imaging through ice what looked like a big crater structure. But they could never sample it. A, they don't know if it's a crater, and B, they have no idea the age. And he just simply said, this is probably the size that the crater would be if there was a Permian crater. The press jumped all over this, and some people, and eventually this guy, to his great discredit, I can't remember his name, said, yeah, that must be it. It must be it. Because it was caused by extinction, or caused by impact, as we all know, there must be a crater. Therefore, that must be the crater. It's really bad science.
So you're seeing it much more of a case, again, of going back to these flood basalts, messing with the atmosphere, basically, global warming.
But that's so unsatisfactory, Carl. It always has been. There's been a sense that the flood basalts were somehow involved for a long time. But what was missing, and what impact had, and the reason we keep going back to impact is the kill mechanism. How could a flood basalt kill anything? Even if you admit to global warming, how could global warming actually kill anything? And here now we're intersecting our modern day. How bad could current global warming be? And is there any lesson from the past that can really help us? And this is where my new book, not so new anymore, Under a Green Sky, attempts to make that connection. I look at the past and try to say, are we endangered now? And the answer to me is absolutely. Absolutely. The whole scenario, which we could lay out here in few minutes.
Yeah, why don't you
we don't have a kill mechanism.
Yeah, this is the death by sewer gas, I guess you could call it.
Yeah, well, it wasn't my idea, but sure was a good one. It's one that it may not be right. Most seemingly good ideas in science turn out to be incorrect, but nevertheless, it's the best thing we have going. It was by Lee Kump, a highly respected geochemist from the University.
He's at Penn State, right?
He's at Penn State, right? And he came up with this idea that it may have been hydrogen sulfide, a very toxic gas that came out of the oceans in big bubbles. I wonder if you remember that horrible incident in Africa where Lake Nyos was the name of the place, and it was a volcanic crater. It's in Cameroon, and in the early part of the 1980s, big carbon dioxide bubbles came out of solution. The lake was super saturated with CO2.
Right. And then it just killed a whole bunch of cattle on the
But it killed a lot of people. Over 1,000 people, if I remember correctly, were killed. Huge number. Big human fatalities. Well, the physics is the same, except at the end of the Permian, it wasn't CO2 that came out of solution. It would have been hydrogen sulfide. So how do we go from global warming to big bubbles of sewer gas coming out of the oceans? And it's pretty quickly done. It goes back to global warming. Why do we have currents and why do we have wind on our planet today? And we know it's because we have a warm tropics and a cold Arctic, and that any wind you feel is warm air trying to go to the cold spot or cold air trying to go to the warm spot. And so too with ocean currents. If we make our poles warm today, and it turns out the physics of the heating of the planet, we cannot warm the tropics warmer than they are now, more than a degree or two, but we can warm the Arctic 10 or 15 or 20 degrees. If we reduce the heat differential, it reduces wind. I see all these wonderful movies about, superstorms of the future. Well, if the future continues as it's going, there will be no superstorms, no America's Cup, no kites, no wind at all. A very calm planet. And that's what happened at the end of the Permian. Sudden heating by the basalts caused ocean currents to stop. Part 2, when ocean currents stop, the delivery of oxygen from the atmosphere dissolved into the surface seawater, carried by currents down to the bottom of the ocean. This is what keeps our ocean oxygenated today. Currents are carrying atmospheric oxygen down to the bottom. No currents, no oxygen on the bottom. No oxygen on the bottom, you start building an entirely different group of bacteria than we have today. It's almost incomprehensible to me how many microbes there are in seawater. And then if you change that over from the good sort of benign oxygen microbes to what turns out to be some pretty nasty sulfur microbes that produce hydrogen sulfide, deep trouble. And there you go. Global warming, current stop, ocean turns anoxic, not only in the bottom, but all the way to the surface.
Right.
And we have evidence for that. And out come the bubbles. They directly cause poisoning and death. And secondly, maybe even more catastrophically, they knock out the ozone layer. No ozone, no plankton. No plankton, base of the food chain gone. Base of the food chain gone, deep trouble. On land.
Yeah.
No ozone, there go your trees.
Yeah, it was really something reading about this in your book, Under a Green Sky. Just that image of this kind of sluggish, viscous ocean with these bubbles coming out, and on the land there's just nothing there. It's amazing.
Can you imagine the smell? Can you imagine the smell? I mean, the only thing worse may have been following a brontosaurus who ate pine needles. It would have produced a tremendous amount of flatulence. But boy, I'll tell you, that just the whole world would have had to have gas masks. And if you didn't, you're dead. Or, luckily, it turns out the physics, and even Kump shows this, it was unequal, the concentration of this gas from place to place. But he's estimated that it was 200 parts per million H2S. It doesn't sound like much, but we can detect it at very low concentrations. A couple of parts per million. We're very sensitive. We know this stuff is dangerous, which is why it smells bad to us. It would have been sufficient to kill a human. That's enough for a mass extinction. That's a death-kill mechanism. And it didn't just happen at the Permian, we're finding out. The evidence is now at several, and perhaps all the mass extinctions except the KT.
Sort of a grand unified theory of extinction you think you've got.
Well, we had one, didn't we, in the 90s? It was impact. And now, the hubris of it all. It's not lost on me, the fact that here we are sort of touting this. Yeah, we finally found the answer. Well, science gets its comeuppance over and over. That right now, the whole theory is hypothesis. Really, it has a lot to support, a lot going for it. A year from now, the whole house of cards may have fallen down, but it's looking robust.
So, can you can you get an idea of the time scale of this sort of thing? I mean, if we are cranking out lots of global warming greenhouse gases for raising temperature, and how long would it take for us to slow down the oceans to start getting a culture of these hydrogen sulfide producing bacteria going? I mean, are we talking? Is this something that millions of years from now would be a problem, or?
Well, that's the $64 question, and the problem. There's lots of problems, always are, but this one is that you're asking how long it took. Well, we know it happened in the past, but it took place probably at time scales that are so fast relative to the accumulation of sedimentary rock. As you well know, Carl, dating rocks is tough to do, and sedimentary rocks especially. We have some estimates, and I've been asked this over and over in public forums. The answer is certainly it's not going to happen in our lifetimes or far from our lifetimes, unless people immediately sort of blank over, oh, well, that's too far in the future. We're talking thousands of years to slow the oceans down. Maybe tens of thousands of years, maybe 50,000 years for this to happen. But nevertheless, happen it did. And it may have happened much faster than that. I mean, there's the wild card. And the second aspect of it, why people shouldn't glaze over.
Right. Yeah. I mean, it's interesting that there's a similar thing going on in terms of how the planet itself goes through climate changes in the past, where people thought the Earth would come very slowly out of an ice age and then go back in, and very slowly out of an ice age, and actually now it turns out that in a few years things can heat up or cool down really dramatically, at least on the time scale of the ice ages.
And the ice core work you're referring to, it was actually done by a colleague of mine early on at the University of Washington, Minzy Stiver, and he walked out. I remember just the look on his face. He said, 10 degrees in 20 years. A global temperature change of 10 degrees in 20 years. That was just, it had to be wrong. It was way too fast. And yet we now know, boy, climate can change fast. And this is why you want to be conservative, because hyperbole does no one any good.
Yeah.
But how long it takes to get into this is scary. And again, this isn't one of those things that it takes what it takes before it gets lethal, because the oceans first go anoxic, meaning no oxygen on the bottom. Well, there goes all the fisheries. As this thing goes out, we start killing the oceans first, and we are so dependent upon the oceans. The land is probably last, but boy, there's going to be repercussions of this.
Do you guys, do people in your line of work deal much with the scientists who put together this IPCC report? I mean, they seem very, relatively speaking, they seem pretty low-key in the kinds of scenarios they talk about, and they only really look out like 100 years. I mean, maybe that's just sort of how, public organizations work.
Well, once again, Chicken Little doesn't do anybody any good. But on the other hand, you've really hit something that's a raw nerve with me. What I'm seeing is that virtually every single estimate about any aspect of global warming, and I'm including ice melting and especially sea level rise, have been way conservative underestimates. They have missed the mark over and over and over again. I was astounded that 3-4 days ago, I read a scientific report, now saying that the thermal expansion of the ocean, in other words, if we just stop all global warming right now, no more gas goes up, so things are just the temperatures of the oceans they are now, we're going to have a 4.5-foot sea level rise from what we've already done. I'd always heard that this was less than a foot.
Yeah.
Now we're looking at 4.5 feet. If this is true, we've got really deep trouble. And of course, we're not slowing down. China puts, according to reports, 1 to 3 coal-fired plants every week.
Yeah.
Australia, I was on sabbatical last year, I saw that the tankers, well, not tankers actually, these are coal ships, big coal carriers, lined up, because Australia prides itself on being green. They say, we don't burn coal for energy, we send it all to China. Come on, we live in one world, you're getting it right back in your face. And they are stripping Australia of all its coal to send to China because China is so thirsty for oil and hungry for coal. It needs the energy. And they have not and will never sign any sort of accord that slows their economy. They and India control the fate of the world, as far as I can see, in terms of its atmosphere.
Oh, boy. Well, I think that we've pretty much gone through an hour just talking about extinctions.
Never got to aliens. Well, let's do it again.
Maybe we
can. A second blog. Blog 2.
Yeah, I'm all for that. So we're going to sign off here, and so I just want to thank you, Peter, for talking. This has been a blast, and let's.
It's been a blast. Well, it was a blast once.
It's been a release of sewer gas. If you for that.
There we go.
In a good way.
Yeah, in a good way, right? We've created a lot of gas ourselves.
Yeah, well.
Hot air is filling my room.
Okay, great. So and hopefully next time aliens.
Great. Thanks so much, Carl.
Okay.
Great talking to you.
You too.